the beautiful formula can be reframed as V in terms of U by expanding, rearranging, and subsequently using the quadratic formula. So expanding and rearranging we get, and substituting into the quadratic formula results in, it's easy to simplify 2 above, and it can be seen that's also the case for P, given that n sub 1 squared plus 1 equals P times K sub 1, and the same for n sub 2 and K sub 2. Adding to that the product of n sub 1 and n sub 2 minus 1 equals P times the difference of n sub 2 and K sub 2. Replacing those above shows that P can be cancelled. Upon simplification of P and consolidating terms within the square root, we obtain the final thing we need to kickstart an infinite descent is to prove that the square of the difference between n sub 2 and K sub 2 minus the product of K sub 1 and K sub 2 equals minus 1. We can prove that in just a few simple steps. Given these known equations, we subtract the second equation to the first. Then we have a difference of squares that can be factored as the sum and differences of its elements. We can easily simplify n sub 1 plus n sub 2 and P, as that's the third given equation. So we got n sub 1 minus n sub 2 equals K sub 1 minus K sub 2. Adding and subtracting n sub 2 at the left of the equal sign, we reach that P minus 2 times n sub 2 equals K sub 1 minus K sub 2. We then sum 2 times K sub 2 at both sides of the equal sign, and then we multiply both sides 2 by K sub 2. But P times K sub 2 equals n sub 2 squared plus 1. And so, at the left side of the equal sign, we got the quadratic expansion of n sub 2 minus K sub 2. So, once proved what we needed to prove, we reached the simplified version of the quadratic root of V. This can be restated as this equation. And that's all we need to see establish an infinite descent, as K sub 2 is smaller than P. And so by finding U and V in a smaller sum of 2 squares, that is the second equation, then we can find the squares of a first equation. In order to find U and V, we need to repeat the procedure. That is, find through Fermat's little theorem the value of m sub 1 squared plus 1 that's divisible by K sub 2. Deduce the beautiful formula for K sub 2, this time involving the variables R and S, and then deduce the second equation for J sub 1, whose squares involve R and S too. Note that J sub 1 is smaller than K sub 2, which is smaller than P. So we need to repeat the procedure as much as needed, which means developing an infinite descent. Through this infinite descent, we might keep descending until we hit a sum of 2 squares totaling 1, 2, or another integer whose decomposition into 2 squares we already know. Once we reach the bottom, the task turns into an infinite ascent until we reach P. Here you see how the infinite descent and the infinite ascent involve the same equations. Once we have the values of A and B for P sub 1, we then also have the 2 squares of P sub 2. And as we have expressed P sub 2 also with other variables, say C and D, then one of the squares is the sum of those variables, C plus D, should P sub 2 be prime, and thus have an unique decomposition into 2 squares. So we can deduce its values and keep ascending until we reach the first beautiful formula, which involves P. When instead P sub 2 is not prime but composite, and C and D don't work, then we should start an auxiliary infinite descent, unless we are lucky and already know the decomposition of all but one of the prime factors of P sub 2. This can best be seen in an example. Let's find out the decomposition into sum of 2 squares of a 7 digits prime 1,299,841. Through Fermat's little theorem, we find that the prime divides 462,779 squared plus 1. And so it must also divide 837,062 squared plus 1. So the beautiful formula for 1,299,841 involves those values and the variables u and v. And we can deduce a beautiful formula for 164,762, which involves the same variables but in a different form. Then we repeat the procedure, this time finding through Fermat's little theorem that 31,507 squared plus 1 equals 164,762 times 6,025. Keep in mind that here 164,762 is a composite number. So we need to apply Fermat's little theorem to its prime factors and then multiply those squares plus 1 in order to have a sum of two squares that's divisible by 164,762. Then we can apply Brahmagupta's identity in order to find the smallest square plus 1 that's divisible by that composite number. Here you can follow the steps of these auxiliary calculations. And so we find the beautiful formula for 164,762 with variables r and s. And we deduce the beautiful formula for 6,025 with those same variables. We apply the procedure a third time, this time finding through Fermat's little theorem that 418 squared plus 1 equals 6,025 times 29. Here again, 6,025 is a composite number. So we need to do the same procedure we did for 164,762. Here you can follow the steps of these auxiliary calculations. So we find the beautiful formulas for 6,025 and for 29. We could stop here as it's easy to find out that 25 equals 5 square plus 2 square. But for the sake of completeness, let's do the procedure for a fourth and last time. Applying Fermat's little theorem, we find out that 12 squared plus 1 equals 25 times 5. And so we repeat the procedure to find the beautiful formulas for 25 and 5. The descent ends here, as 5 is the smallest non-trivial sum of two squares. 5 equals 2 squared plus 1. Then we'll apply those beautiful formulas for the infinite ascent. For the smallest equation, we got that b is either 1 or 2. Applying that, we find out the value of a. When b is 1, then a is also 1. And when b is 2, then a must be 3. We then apply that in the beautiful formula for 29. And we check that those combos worked indeed. So we find out that 25 equals 5 square plus 2 square. Next, we find values of c and d through the next set of beautiful formulas. So d must be either 5 or 2. When we try 5, then c must be 67. And when we apply 2, then c is 27. When we apply those sets of pairs of values in the second beautiful formula, we find out that 6,025 equals 72 square plus 29 square. Keep in mind that 6,025 is not a prime but a composite number, and so have different representations as sum of two squares. So 72 and 29 may work or may not work when plugged into the next set of beautiful formulas. Here we see indeed that s being either 72 or 29 don't do the job. They don't deliver integer values for r. So we need to find out other representations of 6,025 as sum of two squares. Luckily, when factored, it shows that 6,025 equals 5 squared times 241. And as we know that 5 equals 2 squared plus 1, then it's easy to derive through Brahmagupta's identity that 5 squared equals 4 squared plus 3 squared. And as we already have a representation of 6,025, That's enough to find out the decomposition of 241. We'll show below. And if we didn't rely on the fact that 5 squared equals 4 squared plus 3 squared, then we would have had to develop an auxiliary infinite descent with its n-1 prime factors. So we apply the Brahmagupta's identity to find out the values of w and z's. Here we have a simple system of two equations with two variables that can easily be solved when multiply the first equation by 3 and the second by 4. So we can cancel 12 times w when adding them up. And so we find that z is equal 4, and replacing that value in the first equation gives that w equals 15. Now we can find the other representation of 6025 as sum of two squares. Choosing plus and minus signs give us 72 squared plus 29 squared. That is, the values we already knew. Choosing instead minus and plus signs give us 48 squared plus 61 squared. Finally, we plug those values in the other beautiful formula, finding out the pair values for R and S. 203 and 48 the first pair, and 258 and 61 the second pair. Applying those values in the beautiful formula for 164,762, we get that it decomposes as the sum of 319 squared plus 251 squared. So we established that 164,762 equals 319 squared plus 251 squared. But as it has more than one prime factor, and each of them are naturally also sum of two squares, as Fermat and Euler proved, then it has at least another representation as sum of two squares. We are fortunate here again, as it's easy to find out that 2 times 13 equals 26, and that's easily decomposable as 5 squared plus 1. So we could deduce through Brahmagupta's identity the representation of 6,337 using a system of two equations with two unknowns. Fortunately, we can skip that task, as the representation of 164,762 as 319 squared plus 251 squared actually works fine. When applying those values, we get 577 for V and 454 for U. So finally, we apply those pairs of values for U and V in the first beautiful formula, finding out that 1,299,841 equals 896 squared plus 705 squared. That was a longish method to reach the solution, but it does work pretty well. In this slide, we present in summarized form the entire process. We visualize each step of the process, but without the auxiliary calculations. In conclusion, the method outlined in this section exemplifies an infinite descent process, comprising both a descent and an ascent, ultimately yielding the sought-after solution. In contrast to the deductive and numerical combo approach detailed in the preceding section, which culminates in evaluating a short list of potential candidate solutions, this method operates purely on deduction. While we cannot definitely confirm whether this infinite descent mirrors the method devised by Fermat centuries ago, it seems to be strikingly close. In the following section, we will present a slightly simplified version of this infinite descent method.